Hi everyone, and welcome back to the MCAT A series of lectures in physics. In today's lecture, we are going to be covering work. In the previous video, I discussed energy and defined it as the ability to do work. However, in that video, I did not give a proper definition of what work is, which is the purpose of this video. In particular, for the MCAT, you need to know how to deal with the work done by a constant force. I shall also recap what is meant by mechanical advantage, in particular how it relates to work. I will then go on to talk about what is known as the work-kinetic energy theorem, which is a theorem that relates work and energy. In the previous video, I discussed conservative and non-conservative forces in relation to energy. In this video, I shall discuss it in relation to work. Finally, I shall wrap up this video by defining what is meant by power and how it relates to work. Often, the term work is confused with energy. One reason for this is because work in fact has the same units of energy. Work is measured in joules capital J. However, work is not a form of energy itself, but is instead a method of energy transfer. There are in fact a total of two ways to transfer energy, one of which is work and the other which is heat. The other form of energy transfer, heat, will be discussed in the next video. Work, the other of the two energy transfer processes, will instead be the focus of this lecture. For example, just like in the previous lecture, we can consider lifting an object up. In lifting that object, we are exerting chemical energy, the energy that is processed in our bodies. Recalling that gravitational potential energy is mass multiplied by acceleration due to gravity g multiplied by height h, when we lift that object, we are increasing the height h and therefore increasing the gravitational potential energy. Therefore, there must have been some form of energy transfer from chemical energy to gravitational potential energy. This energy transfer process involves work, and therefore we say that work was done. More precisely, we can consider an object of mass m. Let us consider a constant force capital F acting on that object. Let us assume that constant force F causes that object to move horizontally. Therefore, that force F is at an angle theta to the direction of motion. The work done by such a constant force is given as follows. Work done is equal to the dot product of the force vector and the displacement vector. Recalling what the dot product of two vectors is, this is equal to the magnitude of the force vector multiplied by the magnitude of the displacement vector multiplied by the cosine of the angle between both vectors. In this simple example here, we assume that the object is moving horizontally, so the displacement vector is horizontal. Therefore, the angle theta is simply the angle that the force F is to the horizontal. Remember, cosine of 90 degrees is 0. This means that if we apply a force vertically, that can never do work horizontally, because the force vector and the displacement vector are therefore at right angles. They are at 90 degrees. Therefore, work is only done if the force vector and the displacement vector are not at 90 degrees. If the force vector is in the same direction, for example, in this situation the force vector would be horizontal, then the work done would be simply equal to the magnitude of the force multiplied by the magnitude of the displacement. The work-energy theorem, which is also sometimes known as the work-kinetic energy theorem, relates work to energy. It tells us that the net work done by forces acting on an object is equal to the change in that object's kinetic energy. For example, if we stop a car with our brakes, then we say that those brakes have done work because they have changed the kinetic energy of the car. Note how powerful this equation is for calculating work. We can calculate the work without knowing anything about the force. For example, in the case of the car I just mentioned, if we simply know the mass of the car and its initial and final velocities, then we can calculate the work done by the brakes. As another example, we can consider an object being thrown vertically. Let us assume we have an object of mass 2 kilograms. Let us also assume that we throw this object vertically with an initial velocity of 10 meters per second. A typical MCAT question would then be, what is the work done by the object from the time at which it is thrown up to its maximum height? Well, to work this out, we can use the work-kinetic energy theorem. As I mentioned, this theorem tells us that the work done is equal to the change in kinetic energy. It is the final kinetic energy minus the initial kinetic energy. Well, in this example, the final kinetic energy is 0. This is because the final velocity is 0. Remember, kinetic energy is equal to a half mv squared. If v is 0, the kinetic energy is also 0. At the maximum height, as we have seen many times before, the velocity is zero. The velocity has just gone from pointing in the upwards direction to pointing in the downwards direction. At that point in between, the velocity is zero. Therefore, our final kinetic energy is zero, and our initial kinetic energy is the half multiplied by the mass, which is 2 kilograms, multiplied by the velocity squared, which is 10 squared. Working this out, we get that the work done is minus 100 joules. Anytime you get a minus when dealing with work on an object, that means that that work was done by the object. If work was instead done on an object, then we would get a positive sign. More generally, the work-energy theorem can be applied to changes in other forms of energy. As we shall see in the next video when we talk about heat, the work-energy theorem is actually a generalization of the first law of thermodynamics. This law tells us that energy can change both because of work being done and because of heat exchange. As I mentioned, energy transfer is done by both work and heat. Now, I would like to recap what I said before about conservative and non-conservative forces as well as mechanical advantage. In the previous video, I focused this discussion on energy. What does it mean in terms of work? Well, recall what a conservative and a non-conservative force is. When a conservative force acts on an object, no energy is lost from the system. As no energy is transferred, we say that the work done by the system is zero. For a non-conservative force, however, for example friction, we say that energy is lost to the system, and we say therefore that work is done by the system. With mechanical advantage, I already discussed how it relates to work in the previous video. I emphasized the fact that using something like a wedge or an incline can make our lives easier in terms of force. The force needed to lift an object a certain height can be decreased if we use a slope. However, the work done simply lifting the object vertically and moving it using a slope is the same. This is because the definition of work by a constant force is the dot product of force and displacement. Although we have decreased the force, we have increased the displacement. As I showed in the previous video, the length that object has to move, in other words its displacement, is greater. The force may be smaller, but the displacement is greater. Overall, the work done is the same. Finally, I would like to introduce the concept of power. Power is something that we will see a lot of in a future video when we come to looking at electronic circuits. Simply put, power is the rate at which work is done. It is a measure of how quickly or slowly energy is transferred. It is therefore defined as work over time. Again, according to the work-energy theorem, work is equal to the change in energy, and therefore we can also define work as change in energy over time. As power is simply work or energy over time, it has units of joule per second, energy per time. However, again, as power comes up a lot, rather than writing joules per second all the time, we instead define joules per second as a watt, capital W. This concept of power, as I mentioned, is something we will come back to in a later video. To finish off this second of two introduction videos, I would like to now go through typical MCAT questions about work. The first question is again testing our knowledge about conservative or non-conservative forces. It is giving us 4 examples of forces and asking us which of them is non-conservative. Is it gravity, friction, tension, or elastic? Remember, non-conservative forces has to do with energy leaving the system. When the gravitational force acts on an object, it simply causes that object to accelerate to the ground. Energy may be lost due to air resistance, but that is considered a separate force. Recall, tension is the force related to a string or a rope. Energy is not lost or dissipated when, for example, an object is hung from the ceiling using a rope. Therefore, the tension force is not considered a non-conservative force. Finally, the elastic force, which has to do with stretching a spring, does also not result in energy being lost from the system. Stretching a spring can cause heat to be created, and that is indeed a loss of energy from the system, but that heat is not related to the actual elastic force. Instead, as I've emphasized many times thus far, friction is a non-conservative force. When friction acts on an object, it causes energy to be lost from that object. Energy is, if you like, leaked into the surroundings. Therefore, the correct answer is option B. Next, this question is asking us about work done by a constant force. We are told that a force F of 20 newtons is applied to an object. This force causes an object to move a distance of 10 meters. We are also told that the work done by this force is 100 joules. The question is then asking us what is the angle between the force vector and the displacement vector. Remember, displacement and distance are not the same, but because an object is simply moving from point A to point B in a straight line, for example on a smooth surface such as this, the magnitude of the displacement is in fact equal to the distance. Therefore, to answer this question, we simply have to recall the definition of work by a constant force. The work done by a constant force F in moving an object a distance d is equal to the dot product of those two vectors. Work done is equal to F dot d, which, if you remember, is the magnitude of F multiplied by the magnitude of d multiplied by the cosine of the angle between those two vectors, what we're looking for, theta. Subbing in the three quantities that we know, the work done is equal to 100 joules, the force is equal to 20, the distance, which in this simple case is simply the magnitude of the displacement, which is 10, multiplied by cosine of the angle we are looking for. Rearranging this, we get that cosine of that angle is equal to 100 over 200, which is simply a half. Therefore, the angle theta is equal to the inverse cosine of a half, which I hope you remember is 60 degrees. Therefore, the correct option is that of option C. Finally, this third question is in relation to both power and the work-energy theorem. The question is asking us to find the power needed for a cyclist to accelerate from 15 to 20 meters per second. Therefore, we need to find a relationship between power and velocity. Let us recall our definition of power. Power is equal to work per unit time, which, according to the work-energy theorem, is equal to the change in energy per time. As it is only the kinetic energy that is changing in this case, this is equal to the change in kinetic energy per time, or the final kinetic energy minus the initial kinetic energy per time. Now we have our relationship between power and velocity, because kinetic energy is related to velocity. We therefore have that power is equal to the final kinetic energy, which is equal to a half times the mass of the cyclist, which is 80 kilograms, multiplied by the final velocity squared, which is 20 squared, minus the initial kinetic energy, which is again a half multiplied by the same mass multiplied by the initial velocity squared, that is 15 squared, divided by the time it took to go from the initial velocity to the final velocity, which we are told is 7 seconds. Therefore, we know everything on the right-hand side. This is now simple mathematics. Working it out, we get 16,000 minus 9,000 divided by 7, which is equal to 7,000 divided by 7, or 1,000 watts. 1,000 watts is equivalent to 1 kilowatt, and therefore the correct answer is option A. So, let's recap what we learned in this short video. Again, in the previous video I discussed energy, and here I explained how work is a form of energy transfer. It is one of only two forms, the other form, which is heat, which we will discuss in the next video. As work is equal to the change in energy, as it is the change in a quantity, it has the units of that quantity. The units for work is joule. Then, I described how to calculate the work done by a constant force F in moving an object a displacement d. It is equal to the dot product of that force and that displacement. Then I described how work is related to energy. According to the work-energy theorem, work done is equal to energy transfer. For the MCAT, it is quite common for the work-energy theorem to only be applied for a change in kinetic energy. Typically, it is only the kinetic energy that is changing, and therefore the work done is simply the change in kinetic energy. I then recapped both conservative and non-conservative forces, as well as mechanical advantage and how they related to work. In doing so, I emphasized the fact that work is done by an object to the surroundings only by a non-conservative force. Also, using an object such as a slope or an incline to reduce the force causes an increase in the displacement. Overall, the work must stay the same. Finally, I introduced the idea of power, which is equal to the work done per unit time. It is a measure of how fast energy is transferred. Again, this concept of work will become very important when we look at electronic circuits in a future video. In the next video, however, I shall discuss that other form of energy transfer, that of heat. As we shall see in the next video, in a more general context, energy is transferred both by work and heat. Once you feel comfortable with the questions I presented for you in terms of work, you should then move on to the next video. I hope this video has been of some use to you, and I will see you guys in the next one.